Okay, let's start. Welcome everybody. I see lots of familiar faces. It's a pleasure to introduce Tim Barfoot. He is a professor at the Institute for Aerospace Studies at the University of Toronto. I think one of his main contributions to robotics is that he actually makes things work on real robots and tests them in extensive outdoor experiments and even places such as the Arctic. But that's not all. He also has made significant theoretical contributions, and people are interested. He has a book on state estimation that summarizes all of the ideas, the foundations. And more recently, he has been leading, together with me, the odometry undergrad team that has been competing in the self-driving car competition, and over the past 2 years we have been placing first among 8 teams, and the next competition is in June. So,
okay, great. Thanks, Angela. Great to be here. I've never been to the Vector Institute before, although I am a faculty affiliate, so it's nice to finally see what it's all about here. I will make one correction to what Angela said. So although she said that we're co-leading the AutoDrive team, it's actually Keenan who's really leading the team. So we're just along for the ride. Okay, so what are we going to talk about today? I kind of geared this talk around just giving people a flavor for what we do up at UTIUS, although half of the room is actually from UTIUS. So this is really for the other half of the room. So about 2/3 of the talk will just be a little bit of a historical overview of the things that we've been working on for the last 2 years at UTIUS, and then I'm going to spend the last third talking about some more recent stuff and where we're trying to get to next. And so in particular, in the first part, we'll sort of focus on how can we build reliable navigation for mobile robots that move around in the real world. And we'll introduce this framework that we've been working on for about a decade called Visual Teach and Repeat. And I'll do a bit of a deep dive into one particular topic, which is how do we deal with appearance change if we're trying to navigate with cameras. And then in the second half, we're going to focus more on generalizability. So we feel like we're getting pretty good on reliability, but we kind of overfit to particular applications. And so where we're trying to go to next is how do we build navigation that is a bit more generalizable. So let's start with the first part. Even before getting into that, I just wanted to mention for those that don't know, oh wow, that's loud. We do have a Robotics Institute. I'm not sure how to change the volume because the projector has taken over control of the volume for me. Sorry, let me just actually turn off the volume for that video. That will be better. I thought I could just mute my laptop, but the projector took control. Anyway, we do have a Robotics Institute. We've got about 20 full-time faculty working on robotics around different areas in the city. For those that don't know, we do have some robotics activities here on the St. George campus. I actually hail, and Angela also comes from UTIUS, which is 20 kilometers north in the city. And we have a growing cluster of computer scientists also in robotics at the Mississauga campus. A little about me, just to give you my trajectory. I actually did all my school here at U of T, so as they say, I bleed blue. After my PhD, I left and I worked at a company called MDA. It was called MD Robotics at the time, Spar Aerospace before that, and it's the company that builds the Canadarm space manipulator. I didn't actually work on that program, but I worked on a number of navigation projects related to mobile robotics, including underground mining, planetary exploration, and military robots. After that, I came back and I started my faculty position at U of T. So for the last 13 years, I've been at UTIUS as a professor, working on all kinds of different projects, and we'll get into some of these throughout the talk. I did my sabbatical a few years ago at Oxford, where I wrote the book that Angela mentioned. And then about 2 years ago, I took a break from U of T and I moved my whole family down to Silicon Valley, and I worked on a very interesting project at Apple that I can tell you nothing about, but it was good fun. But decided that wasn't the long-term plan for me, so I've now come back. And we're trying to grow this Robotics Institute, and now I'm happy to be also affiliated with the Vector Institute. And so what do I do? I'm mostly working on navigation for mobile robots, or mobile robot autonomy. I kind of break this into 3 main spheres. State estimation, which involves things like perception, localization and mapping, tracking things, path planning, and a little bit on control. And so the size of the circles kind of indicates a little bit how much time I've spent on each of these different topics over the years. And just to give you a few examples in each of these areas, in the planning sphere, we have worked on things like sample-based motion planning algorithms. So some of you may be familiar with something called the RRT star planning algorithm. We did some extensions to that called informed RRT star and bit star, which actually made RRT star tractable in high dimensions so that you could use it for things like manipulation planning. We've done some work on localization and mapping. And this is just showing one video from a project that actually more of a framework that we've developed where we consider robot trajectories to be continuous functions of time. And we found that there were some really interesting connections to Gaussian process regression. You can kind of show that all the key state estimators that we use, like the Kalman filter and the RTS smoother, are just instances of Gaussian process regression. This turns out to be useful for dealing with, for example, sensors that have motion distorted data. With Angela, we've done a little bit of work on control. So this is an interesting project where we're trying to get a robot to track a path really accurately at high speed. And we've had different flavors of this, but in the most recent version, the idea is the robot is driving, and with its camera, it can measure its path tracking errors. And based on those errors, it can actually learn a better model of itself from that data, redesign its controller with the improved model, and then try to drive again with that better model. And it kind of does this iteratively. So after a few drives along the same path, it's able to drive much more quickly than in the first case, where it just had an approximate model of itself. And then the thing that I'm going to talk mostly about today is this overall framework called Visual Teach and Repeat, which involves elements of all of these spheres. So this is, I'll get into this on the next slide, actually. So what is this Visual Teach and Repeat framework? Basically, it's a full robot navigation stack that allows a robot to navigate using only vision. And I like to say this particularly in a machine learning crowd. It uses one laptop, one camera, one training example of every path, no GPS, no IMU, no DNNs, no global map, and no semantics. Okay, and so the idea is we go to a new environment, such as this mining environment here. This is a disused open pit mine. And we manually drive the robot around on all the allowable paths we would like it to operate on. This basically defines a graph with nodes and edges. And as we were driving, we built a visual map that allows us to navigate on each of these edges. So that's called the teach phase. We then give the robot the map, and it's supposed to begin to operate on this graph basically forever. That's the goal. So using only cameras, it tries to reference against this graph of edges and nodes in order to figure out where it is, and then drive the path. And so you can see the robot there. It's driving, it's actually just climbing this hill right here. And then it's going to come around the corner and then descend down this big hill. So all of this, I'll just stress again, is using one camera, one laptop, and it's not using GPS. And it's fully autonomous. So we've been working on this for about 10 years now. This is sort of where we were at approximately 4 years ago. Even before that, though, even in the early days, 10 years ago, we were, as Angela said, we'd done some field testing up in the high Arctic. So my original motivation for working on this was planetary exploration. And this is a mock Mars site that's run by NASA up on Devon Island. So we did some testing way up there. It was very fun. The logistics of trying to get robots into the Arctic in small twin otter planes is, you can ask me about that after, but that was good fun. We even delivered some of our code to the Canadian Space Agency, and you can see some of their rovers being navigated on the Mars exploration, or Mars emulation terrain at the Canadian Space Agency in Montreal. And then this is actually an interesting experiment we did where the robot was using this visual path following essentially as a backtracking tool. So it was actually trying to find its way through an unknown environment. And every time it got a dead end, it would use this backtracking technology to sort of come back and then branch off a tree that it was growing. So you can kind of think of this as like a physical embodiment of a tree search algorithm that's enabled by this path following. There are some commercial applications of this technology. So even before, when I was in industry, we were looking at using this visual teach and repeat framework to navigate large mining vehicles. So just to give you a sense of the scale, the size of the wheels are basically my height, this vehicle. So it's a 50-ton vehicle. It's navigating, in this case, not using cameras, but lasers. There's nobody in the vehicle. So this is an operation in some mines in Sweden and Finland. And basically, it It allows the robot to drive back and forth between a pickup point and a drop-off point, and then an operator basically takes over when it gets to the pickup point to load the scoop, because the scoop is that's a bit difficult. In fact, we've got a mining person in the audience, I think, that will attest to that. With Anglo, we've been putting this visual teach and repeat framework on UAVs. So this is a DJI M600. Some of the students in the room are working on this project. And the idea is to use this visual teach and repeat as a fallback in case GPS were to fail. So here we're seeing an outbound flight that's under GPS control. And the robot is doing this. It's basically teaching one of these paths to itself by storing all of these surf features. And now it's in fully autonomous mode where it's backtracking. So now it's using vision for localization, not GPS. And so we have all of that running on a small board in the air with a gimbaled camera. We've even taken some of these technologies around localization and mapping and put them on the TTC subway trains. So we went down into the subway when it was not operating in the middle of the night, and we attached a planar laser rangefinder scanner to the front of the train. And then we drove through the tunnels and we actually built a map, which you can see is all of this gray stuff here. And then we drove the train through the tunnels again, and we localized our live laser scans to that map. And so why would you want to do that? It kind of seems like a pretty easy problem because the train can only move in one dimension. It turns out the way we position trains, the TTC trains right now, is using something called RFID tags. And it means that the precision of that localization is about 100 meters. And because the precision is so low, they actually have to keep the trains quite far apart because they're not that certain about where they are. And if you could improve the precision of the localization, it turns out that we could actually put twice as many trains on the same tracks that we have right now. So just by improving localization, you could do that. And we showed that we could actually position everywhere in the tunnel, this was on the Shepherd line, to about 10 centimeters. So if this were to make it through all the hardening of the software and make it safety critical, you could actually put twice as many trains on our TTC system. So we've been working on this navigation stuff for quite a while now. This is my growing gallery of robots that we've deployed this algorithm on. Everything from planetary rovers to military vehicles like this tank-ish thing, this UAV. And it's gotten to the point now where one of our partners, ClearPath Robotics, has taken ownership of our code and has now offered this as a commercial software product that you can buy integrated onto their robots that they sell. So that's their Warthog platform with VT&R implemented on it. So you can imagine over 10 years, we didn't just do one thing. We worked on a lot of different extensions of this technique. I showed you a video of trying to learn to improve path tracking. I won't get into the details of that too much more. We've also learned to assess terrain. So given that you've built a map, you kind of want to know if it's still safe for the robot to drive on these paths during operation. So we can use computer vision, of course, to do that. And it turns out it's actually pretty difficult to do that in some kind of scenarios like tall grass, because the geometry is a bit confusing if you just use geometry. So we did a whole branch of projects around assessing safety for the robot to drive. We even looked at the idea of, in this graph of edges and nodes that we can drive on, some of the edges tend to be more reliable for things like localization, or perhaps they get blocked by parked cars and other vehicles more often than others. And so we actually posed this as a planning problem where we wanted to get from one place in the graph to the other, where we had a reliability associated with each of the edges in the graph. And to my great delight, it turns out that you can pose this as something called the Canadian traveler problem. And so there's actually a nice solution for how to solve that problem. And you end up getting a policy for how to operate on that graph. And the thing I'm going to spend the most time talking about now is how to deal with appearance change, because that's kind of been the thing that's been the thorn in our side for the last several years. So to talk about that, let's get a bit more into the details of how VT&R works. So I'm going to go back now to the teach phase. And the idea is, as we're driving the robot to define one of these paths, it's being driven manually, and we're estimating our motion using visual odometry, in this case from a stereo camera. And so we can estimate the motion transforms between all of these edges, and we store those. And we also store the landmarks that we observe, in this case, something like triangulated surf features. And this is critical. We store them relative to where they were first seen. We don't store them relative to some global reference frame. So by storing them where they were first seen, we have what's called a relative map structure. There's no privileged reference frame in which everything is expressed. And then the nice thing about that is it has the property that if you were to rubber band a section of that map, you don't need to do anything except to just sort of cut out the bits that are not inside your rubber band, and then you can kind of think of the world as just being what's inside this rubber band. And so if we're trying to repeat the path now, and we have a new pose, all we have to do is re-observe some of the landmarks that are in our map, and then we can determine the transform between the live pose and the pose that's in the map. And then if we move, we may or may not actually get some more matched landmarks, but we can always estimate this using visual odometry. And then we can move a little bit more. And maybe now we reacquire some features, and we can determine the transform directly between the live pose and the one in the map. And so this just progresses. Once we know where we are, we can, of course, do another rubber band for control. So we can run something like model predictive control, where we look at the shape of the path ahead and try to figure out exactly what commands to apply to the vehicle, get it back onto the path if it's a little bit off. And so basically the lesson for all of this is that a lot of robot navigation is really just a local decision-making process. We don't really need global information if all we're trying to do is do something like track a path. And so I kind of like to explain relative map structure in the context of this picture. The idea is that we don't have any particular global reference frame that makes the whole map make sense. So it's a bit like the Escher staircase. If you just look at one of these corners, everything makes sense. Right? Locally, it makes sense, and you could use that to navigate. But globally, it does not add up to something sensible. And the same thing is true in our map, actually. I showed you some paths that are actually closed loops. We actually make no attempt to make the local transforms add up to identity transform around that loop. It just doesn't matter to us. We just tell the robot, if we come back to a place we've been before, we just tell it, this is the same place. Put an identity transform between these two poses, but it doesn't have to add up to identity transform all the way around the loop. And that's good enough to let the robot actually make local decisions in order to drive on the path. Okay, so let's go back to appearance change now that we know a little bit more about how VT&R works. There are, of course, lots of dirty tricks that we can pull to try to overcome something like lighting change. So imagine we're trying to navigate using cameras. As lighting change happens, it becomes quite difficult to match things, for example, in the middle of the night to the middle of the day. So we could actually do something like change the sensor. We could swap out cameras for a lidar, and we looked at that. You can actually make that work, but lidars tend to be expensive. You can do things like classical computer vision techniques, like color constant transforms. So you can combine the red, green, and blue channels in clever ways to sort of remove the effect of lighting and just provide the material property of what you're looking at. So you can kind of see here, that's removing the shadows in the images. Then we can operate on these images instead. We can even do really simple things like just put more cameras on the robot so that they're pointing in different directions so that when things like sun flares happen, they tend to not affect all of the cameras at the same time. So these are all really band-aids on the problem, I would say. At the end of the day, we're still trying to match this pose to here. And if this matching function fails, we're kind of cooked. So what to do? Really, what we want to be able to do is match any of these conditions to any of the other conditions in some clever way. So these are all the same place over a 24-hour cycle. And just to sort of underscore, I'm just going to cycle through, I'm going to randomly sort the order of these and just display, as we're driving along the path, all the different things that we might see. And so the goal is to be able to drive under all of these conditions without having to do some massive data collection and training procedure. And just as a bit of a spoiler, it turns out we can do this using nothing but surf features, which might sound a little bit surprising. There's a trick to it, though, which I will reveal later. Okay? But just realize that using only surf features, we can drive fully autonomously across all of these lighting conditions. We can also do it over other types of appearance change. So this was an experiment where we plot a path in the fall and continue to drive on it all the way through the winter and into the next spring. And so you can see there are some pretty extreme differences in the way this path can look. Bright sunny days to snowstorm in the dark. And really we want to be robust to all of those things. And again, in this experiment, we drove 100% autonomous using nothing but surf features. Okay, so there's got to be a catch, right? How could we do that using just point features? So this is the trick. So this is the same place. This is actually the Canadian Space Agency's Mars emulation terrain, and this is different by about 7 hours. And you can see there's quite a bit of difference. There's a huge shadow cast by a tent that's down here. Things over here look quite different, and you can see we can get a small number of matches, but even after 7 hours, surf features are starting to fail. It's really difficult to match these things. And so the trick, I'll let that play for a sec. The trick is, what if we didn't wait 7 hours before driving the path again? What if we were to split that interval in half and drive 3.5 hours later and then 3.5 hours later? And so what we do is we have this idea of having bridging experiences. So we teach the path, and this is the experience that's built into the map. Then 3.5 hours later, we drive and we see this experience on the bottom. We can probably match those things fairly well. And then all I have to do is take the later experience and match it to the bridging experience. And if I can get some matches back to the original experience as well, why not? So this is the idea of chaining things through time. And if one intermediate experience is good, 2 is surely better. Right? And if 2 is good, surely 4 would be better than that. And so the idea is that all we have to do is not let the world change too much before we acquire another experience and embed it in our map. And I will just stress that we only have to drive the path manually this first time. The rest of this data collection happens during autonomous operations. And I think that's key for robotics. We don't want to have to gather enormous training data sets before we can even start to move. That's a problem for us. So basically what we've done is we've taken this relative postgraph structure where I've now removed the landmarks because it's a bit too cluttered if I leave them. And the first time we repeat is here, and now we have 2 experiences in the map. Then the next time we have 3 and 4, and eventually we have 5. And now we use the same rubber banding trick that we did before, only now instead of just a spatial postgraph, we have what we call a spatiotemporal postgraph. And the idea is that all of the black triangles are already well localized to, say, this one. And then if I want to know where the red triangle is relative to this black one, even if I have no direct matches between these, as long as I can match to some of the things inside the rubber band, I can actually figure out where I am metrically with respect to the path. And so that's kind of why this works. It's the idea of not just trying to build one model of the world, but rather have several models of the world that we can match to, have them all related to one another. And of course, where do you stop, right? If you save an experience every time you drive, you could get up to hundreds or thousands of experiences. So of course, at some point we'll need to prune. But even before pruning, it turns out that there are some really clever techniques that we can use just to quickly identify good candidates for matching to. So we don't really need to match to all of the previous experiences at once. We can use some kind of triaging tool to pick, say, the best 5, and just do the detailed localization against those 5 experiences. And so we looked at a couple of ways of doing this. One of them was just based on bag of words. So we would just quickly do a whole image descriptor, where we would take that and then quickly match against the other experiences. And then whatever did well against that, we would do detailed localization against those. We also looked at another technique that was actually based on, inspired by a Netflix movie recommender system. So you can kind of think of the different experiences as users. And so if Angela and I both enjoyed a couple of movies in the past, and then she watched another movie, it's likely that I'm going to like that movie as well. And so if 2 of the experiences are matching features well in the past, it's very likely that they're going to match again. So we've looked at the idea of using collaborative filtering to figure out to recommend which experiences to try to match against. And then you can scale actually up to even 1,000 experiences and run in real time. You might also ask, what about storage? Storage for these techniques is about 40 megabytes per kilometer. So really, we're not hitting anywhere near disk space, because we're really just storing the surf features, not the raw images. And so putting that all together and going back to this first video that I showed you, VT&R turns out to be a pretty accurate way to navigate around in the world. I will just stress, you see these tracks in the ground? Right? Those are actually not there when we started. Those are there because we taught the paths, and then we started driving them for 2 weeks in this field experiment. And we tracked the paths so accurately so many times that we actually developed ruts in the ground. For me, that's reliable robot navigation. It's predictable and it's reliable. One camera, one laptop, no GPS, no DNNs. Okay, so that was sort of the state of the art about 4 years ago. I'll tell you about a couple of other things that we've done to try to deal with appearance change that have not really made it into the main branch of the code yet, but are still kind of interesting. So I said that we were using surf features. Surf still works pretty well. We implemented that on GPU about 10 years ago, and I think the OpenCV implementation of GPU surf came out of our lab. But there are other descriptors that are out there, and we've compared to all of them periodically. We always seem to come back to surf features. But one of them was quite interesting. If you're familiar with brief features, what they basically do is for every feature, we're taking a little patch, and instead of using a histogram of gradients like in surf or SIF, what they do is they they have a pattern of binary comparisons. And so each of these lines, this is not actually this big, it would just be centered around one of these small features. The descriptor for that particular feature is just a concatenation of these binary comparisons. So for every edge you're seeing in this picture, they just compare the intensity at one end to the other and say whether it's higher or lower. If it fires, then you put a 1 in the descriptor, and if it doesn't fire, you put a 0 in the descriptor. So these have been quite useful. So the plain vanilla version of that is called brief. And what we looked at was an extension of that called brief, which I actually forget what the acronym is, but the idea is that you try to evolve the pattern of binary comparisons in order to overfit essentially to your environment. So in other words, to learn the pattern of binary comparisons that work well for your type of data. And it turns out we can do this while we're driving. And the reason we can do that is we can essentially self-supervise. Because many of the binary comparisons will survive ransack in our motion estimate, we can then use that motion estimate to kind of label or score the other binary comparisons that we didn't use and decide whether they were good ones or not. And then we can run something like a genetic algorithm that basically considers this to be a population of individuals, and we basically do survival of the fittest. So the binary comparisons that explain the motion well get a high fitness, the ones that don't get a low fitness, and then we kind of cull the ones that get a low fitness and then randomly give some new ones. And it turns out you can actually just do that while you're driving, and you'll end up with a better feature detector that works for your environment. So that algorithm is not ours, but we tried it for our problem, and it worked reasonably well. Normally, brief is using a pattern of binary comparisons that kind of looks like this Gaussian cloud of points. After running this algorithm for a while, basically what happens is you get these shorter binary comparisons that spread out in the patch more. And so that's kind of interesting that you can kind of go from this to this. My student got very excited when that happened. And then I looked at this and I said, well, really all it's trying to do is make it look like surf. So I proposed a handcrafted set of binary comparisons here that we call Asterix. And it turns out Asterix does better than all of these, even though I just handcrafted it. Anyway. It does turn out that if you use these techniques, you do get a lot more useful matches. So we get, I would say, in feature-rich environments, we get about the same as surf, but in feature-poor environments, we tend to do quite a bit better. We've done a big comparison against all the different kinds. We still use surf, though, just because the gains are not as big as they might be. So another thing that we've been looking at, this is actually Angla's master's student, Bhavit Patel. We've been looking at trying to get away from features altogether. So in our UAV project, we struggle quite a bit in using point features. And we've been even trying to look at the idea of not just teaching the path directly from the sensor, but perhaps virtually teaching a path to the robot by flying it through Google Earth rendering. And so we could take a sequence of images from Google Earth and try to match live camera images to them. And it works for us because we can actually, because we know the flight path that we want to fly, we can actually render images along that path and then try to match against those in flight. But these are captured by a totally different modality. It could be satellite images versus camera images on a UAV. Trying to match those directly with point features just doesn't work very well. So we've been looking at the idea of using mutual information to match this. And the idea kind of goes like this. We start with the images at their proposed alignment, and then we sort of run an optimization procedure to maximize the mutual information between the images. And the output of that is the offset between the images in some kind of three-dimensional space. And that tends to work pretty well. Here's just a flight path where we were able to match all the way around. And then the real clincher is, does it work under something like lighting change? So we did an experiment where we flew sort of 7 times throughout the day on a sunny day. And so the shadowing can change quite a bit, and we tried to match against the same Google Earth renderings. And it turned out to work pretty well. We don't actually have this running online yet. But here's just to give you a sense of how much the appearance of the world can change throughout the day. You can have massive changes in the shadowing. It turns out that that is kind of a problem for some parts of mutual information. But if we filter this with our standard sort of Kalman filtering type framework, the answer looks good enough that we could probably stay on the path. So we're looking at trying to get this in the loop on our UAVs next. And then the last thing that we've been looking at somewhat recently is, could we actually leverage deep learning to try to build a better feature matcher? In fact, what about just skipping the feature matching altogether and just try to take 2 views of the world and directly output the pose offset between them? So could we regress on pose to try to just solve the localization problem directly from the images? The question for that is, how do you get the training data, right? I'm just proposing this as a supervised learning problem. How would you get the training data? And so the idea is we already have a solution for this, which is the multi-experience localization that I told you about before. So the idea would be to then take the localization that we already have labeled from our other classical algorithm and then use that to try to train a DNN to do this. So we kind of think of this as like compiling all of the experiences that we have of the path into a single matching function. And this works okay. We don't have it running closed loop on the robot yet. We've tried this for visual odometry with mixed results. So sometimes good matches, sometimes not such good matches. But really the core of the problem is how well can we localize against previous experiences. So this video is going to show, this is what the middle column is what the teach images look like. The left column is what the repeat images look like. And the right-hand column is sort of showing an alpha blend of the 2 at the outputted pose from the network. So if the alpha blend looks good, if the images are matching, it means we've done a good job at localizing. And it tends to do okay. It's giving small pose changes, so it's not like a large pose change problem. We're always fairly near our path, so it's usually quite a small pose change that we need to output. And this looks okay. It still does not look, of course, it's never going to be better than the labels that we used because it was a supervised training problem, but it's getting close to the quality of the multi-experience localization. We're kind of encouraged by that, but we think there's still a ways to go. For example, taking that solution and trying to use it on a totally different path is an open question, right? So we use the training data from one path. It's not necessarily going to work on another path, so we're kind of doing those experiments now. Okay, so that brings me to the end of the reliable robot navigation and kind of what we've done up till now. And I just wanted to spend a few minutes talking about some of the other ideas that we've been looking at moving forward. So this is more of the ranty, speculative part of the talk. So this is my graph of where robotics is. I kind of feel like there's some trade-off that we always try to strike in robotics between the difficulty of the task that we're trying to solve and the generality of the solution. And of course, we would all like to be at this dot in the upper right-hand corner. And I would say that a lot of robotics has kind of taken this path of trying to focus on trying to get good at some of the difficult problems. So many of the things we've shown you here are pretty difficult navigation problems, but they're not super general, the solutions that we've come up with. So for example, we can only drive on a path. So we couldn't necessarily just go into a brand new environment and just randomly drive. We also probably could not just change out the sensor and then use the same software to make that work. So we could consider continuing along this path in robotics. I'm kind of at a personal crossroads where I'm thinking about trying to make a beeline towards this idea of more general solutions. And maybe in the end, I'm going to end up somewhere between these 2 dotted lines. But it's really kind of an open question for me. In some sense, my lab has forked. Some people are continuing to push VT&R and make it better. And others are now looking at this idea of how do we do something more than that. And so really, my mission statement is I would like something like VT&R to work for any rich sensor, camera, laser, radar, RGBD camera, on any robot platform, flying, driving, swimming, walking, in any scene, which means all lighting, all weather, all geometry, dynamic obstacles, indoor, outdoor. Minimal programming effort for a new robot and sensor configuration. So right now it takes probably a couple of years to engineer a really robust piece of software to navigate around outside. With only a single training example of every path, which is actually true right now. We only have to show the robot the path once and it can continue to drive on it. With minimal onboard compute, so I don't want to put a server on the robot, although I'm happy to use a server to do training, and without requiring an expert user to operate the robot at all times. So that's kind of the mission statement. And so what I've kind of proposed to the lab is what I'm calling the Mr. Potato Head challenge. And so the idea is Mr. Potato Head is kind of this modular guy who you can attach different feet and hair and things to. And so what I'd really like to be able to do is build something like a visual teach and repeat algorithm where you could take any rich sensor, attach it to any mobile base, drive around to get some data without a lot of expensive ground truth, and then from a template, auto-generate the VT&R algorithm for that Mr. Potato Head combination. That's a big challenge. I think it's not something we're going to solve right away, but I'll give you some ideas about how we're approaching the problem. So for me, the first-class citizen in all of what we do is the graphical model that underlies our mathematical explanation of what the robot is doing. So we can kind of think of the robot as having some kind of state, which are these x's, and we don't really know what those are. So that's our latent trajectory. We apply some commands to the robot moves, which generates all of these x's, and then we get some sensor data. And really, most of the problems we're interested in are tied to this graphical model in one way or another. State estimation, calibration, planning, maybe even control if you think about it as model predictive control. Even something like linear quadratic regulator you can cast as a problem where you're doing inference over this graphical model. And really the question for me is, one of the pain points I would say in robotics is we often have to start with these models, right? The motion model and the observation model of the robot. And really what we'd like to be able to do is only start with the graphical model and fill in all the details just from the data. That would be great. So for example, in the VT&R problem, maybe I've got some past control inputs, some past sensor outputs, the current time is right here, and I want to make the sensor output look like the map images, and I'm doing inference over the commands that I would have to apply to the robot in order to make the output of the robot look like the map, just as one example. And so I started looking into this, and it turns out that, of course, people have thought about this idea before. Zubin and Dear Sam had looked at this problem 20 years ago. In fact, I started leafing through this paper, and they have an exact picture of that graphical model that I was just showing on the last slide. And they've looked at this idea of essentially trying to express the motion and observation models of the robot as neural networks, but then still maintain the graphical model and do inference over the latent state using more classical techniques. So I'm really interested in this idea. Of course, 20 years ago, they didn't have all the same deep learning tools that we have today. And so basically what we're heading towards is trying to revisit this idea in the context of modern machine learning. And really the nice thing is you can essentially pose this as a variational inference problem. And the E step basically gives you a distribution over the latent trajectory, and the M step, an expectation maximization. The M step allows us to sort of, given that distribution over the latent trajectory, do some tuning on the parameters that express all of our models. And we can do this, basically Sam and Zubin showed that this was a good thing to do and that they could make that work on some simple problems 20 years ago. If we start thinking about maybe using something like a deep neural network to express what those models look like, in the E step, we really don't want to have to take the derivative of a deep neural network with respect to the latent state in real time. That would be an expensive operation to do. And so we started thinking about how could we avoid that problem so that we could just do forward passes of the neural networks and basically leverage the hardware accelerated inference stage of using DNNs. And so we put a paper out in the fall proposing a new inference framework that we call exactly sparse Gaussian variational inference, which is a general technique to do inference on probabilistic graphical models, where we exploit all the sparsity in the graphical model. We basically showed that we could make this tractable. And so if you think of it from a robotics perspective or a computer vision perspective, we've generalized MAP estimation, which in something like bundle adjustment uses the sparsity of the graphical model to make the solution efficient. We can now do that in a variational setting. And so if you're interested, you can check out this paper on arXiv that shows how that can be done. But the summary is we basically find the best Gaussian mean and covariance in terms of divergence, scale divergence from the true posterior. We show that it's tractable by essentially leveraging the graphical model and the sparsity in it, and we can do it even when there are loops, so our graphical model can be loopy. We also show as a byproduct of this that a bunch of expectations have to be computed, and instead of using the derivatives that we normally do in maximum a posteriori, we use Gaussian quadrature. And so we can essentially take something like the sigma point Kalman filter and now use it as a batch inference framework. So we can do inference without computing derivatives of any of the models. And the implication, of course, for that is if you had a DNN representing one of the models, you now do not need to take the derivative of it. I know derivatives get used in backprop, but I don't want to take derivatives of the model with respect to the latent state at runtime. And so just a few teasers on how we've made progress on this. Just doing the E step, so just forget about, we've got known models for the robot. Does this framework actually work to do just state estimation? So we're just trying to actually estimate, in this case, the trajectory of the robot and the positions of all of these landmarks. So it's a SLAM problem. So we show that this exactly sparse Gaussian variational inference does in fact work well and is tractable on these SLAM problems. And it even turned out that by posing it as a variational problem instead of MAP, we actually did a little bit better than the classical SLAM solution on a highly nonlinear problem. So then the next step was we wanted to see if we could also learn some model parameters within this framework. And so this was work that I did with Angela, and Jeremy Wong is somewhere in the room. So he's the lead author of this paper that was just submitted just 2 weeks ago. And the idea here is we're not going to learn the full robot models yet, but maybe we could try to learn all of the noise parameters of those models. And so we drive around this car, we've got Velodyne lidar data, and we're matching to a HD map. And we take all of that data and we essentially do inference over the latent trajectory. And then we also do inference over the covariances of each of the measurements. And then we use priors on both of these. So the prior on the motion model is actually a Gaussian process, which I alluded to earlier. And so we're learning the hyperparameters of that Gaussian process model. And then the prior on the covariances is we actually use an inverse Wishart prior, which is connected to the idea of doing outlier rejection through a Cauchy robust cost function. And so we also learn the parameters of that inverse Wishart prior. And so with no ground truth, just the data from the robot, we can drive around. We can do a pretty reasonable job of learning all of the covariance parameters and estimating the trajectory of the robot at the same time, which I think is a big step forward. It means this is actually kind of a pain point when you're using these kind of estimation tools, is how do you come up with the covariance parameters? And we were able to do that even in the presence of a large number of outliers, which was a little bit surprising to me. And then very hot off the presses, just from 2 days ago, so don't get too excited about this, we started to think about, could we actually learn the whole robot model? So in this case, we're using a very small neural network. It's like depth 5 with input 2 and output 2 to learn a nonlinear range bearing model for the observation model of the robot. So this robot is driving around. In this case, it knows where all the landmarks are. It does not know its own trajectory. It does not have ground truth. And it needs to learn the range-bearing sensor model. And that includes where is the sensor mounted on the robot. And it turns out, just by driving around and taking the data, we can actually do a pretty good job of localizing the robot, even though we didn't know the sensor model to begin with. It learns the sensor model. And so the network started with random weights, and it learned something that was good enough to actually do a good job of localizing against the map. But it's not super great yet. It's still kind of inconsistent, and I think there's still some work we need to do. So that's kind of just a quick tour of this Mr. Potato Head challenge that I've posed. Really what I want to get to is the point of using a rich sensor, not some simple range-bearing model. But we have a new radar that we just submitted a PO for. It's going to show up soon. I'd like to stick that radar on top of a new robot, drive around, and and then auto-generate a teach and repeat algorithm for that sensor on that robot. Is it possible? I don't know. Are you excited about that idea? Come and talk to me and join the fight. And so I'm just going to stop there. And I just wanted to put this video up because I was very entertained by it. This is some work that I did 20 years ago that I happened to find the video for while I was making this talk. And so this is a robot that's actually using reinforcement learning with feedback from a physical encoder on this treadmill. As it tries to walk and makes progress, it's a reward signal and it tries to figure out how to walk. So we were doing that 20 years ago on the hardware. So I'll stop there and take any questions that you have.
Thank you. It's all very interesting. I have sort of a high level and probably a naive question, but as soon as when you're correcting your paths, like let's say going the second time through something you wrote the first time, and you do the correction, how do you sort out the scale of the correction? That is, you don't want to see a little bump on the right, you turn so far to the left, you crash into the fence, right? So how does the scale of the correction kind of get calibrated, especially the first time you're correcting?
Let me see if I understand the question. So how does the scale? Okay, let me go back to this picture.
Like if you learn something like if there's a problem here on the right, so you have to go a little further to the left, how much correcting you do because you haven't been further left the first time. So.
Yeah, so because where did that part of the talk go? Let me just go back to this picture. Right, so when we're localizing, we're not really just trying to directly learn the command to the robot. We actually solve for the 6-degree of freedom pose of the live view of the camera against the map. And then we use, say, model predictive control to try to zero that error. So it doesn't matter. The controller is designed to basically work with the robot being anywhere with respect to the path. So if we can tell the controller where we are with respect to the path, it figures out what to do to get back onto the path. That's more like classical control. We're not directly regressing on the commands that we apply to the robot. And so that's one nice property of classical control is that it's all model-based, so we don't really need to have experience of being in every error state.
That's what you as a little part of it.
Yeah.
That's supposed to be the thing that you're integrating, or why is that?
Normally, if we're doing more classical technique for state estimation, like the Kalman filter, something like that, you end up having to take the gradient of your motion and observation models with respect to the state in order to pose it as an optimization problem so that you can try to figure out what the state is given the.
Is it that you don't do it? What does that mean?
That I don't want to be doing gradients. I don't know. That really isn't the main point of it, but I feel like if we didn't have to do gradients, then it just sort of makes it cleaner to implement.
You don't have to worry about optimizing.
Yeah. Okay, yeah. So like if you have the model in closed form, taking the gradient is straightforward. But if the model is, say, a neural network, it would be nice to not have to. It'd be nice to use like existing software to inference on that network, where I can just use the forward pass. And so I don't really want to have to like rejig TensorFlow just so that I can take the gradient with respect to the latent state during the forward pass. It's sort of a side benefit. I'm sure there's a way to do that. It just means then having to like open up that can, the sort of mesh our framework with.
And one last question. You said in your ideal world you want to learn from one run.
Mm-hmm. Well, I want to be able to drive the robot around for some period of time in order to learn the models of the robot. But then when I go to a path, I only want to have to show the robot one example of that path in order for it to automatically drive on the path. So there can be
your model
it could be a more extensive. No, I'd like to learn a generic model for that robot.
Okay. Yeah. Because.
So it might take lots of driving around in order to learn the model. But then when we go to a new path, I don't want to have to manually show it 1,000 examples of that path. That's not practical.
Why do you think you need one example of the path if you know them all?
Well, you have to define the reference that you're going to track against, right?
Okay. Any other questions? Okay,
Okay, thanks for coming.